Hello and welcome. In this video, we're going to be talking about points of inflection. Now, this is another application of our second derivative, right? In our last lesson, we talked about the second derivative sort of being our concavity function, right? Our first derivative is our gradient function, and our second derivative sort of measures concavity along a curve, right? Now, before you jump into this video, I really want to make sure that you try and have that well thought out in your brain before we move on, because it'll make a lot more sense when we talk about points of inflection in this video, okay? So, all right, when our second derivative is greater than 0, our curve is concave up, all right? So that's like this section here, all right? You can see where it's basically like a bowl pointing towards the sky. If it's less than 0, our curve is concave down, all right? And so that's like this section over here. The curve is pointing, the concavity of the curve is pointing towards the ground, okay? And then we had the special case, which I didn't quite touch on, all right, as to why we only have a possible point of inflection when the second derivative is equal to 0, okay? All right, so in general, if the second derivative is equal to 0 and concavity changes, all right, we would have a point of inflection. However, I'm going to show you in an example as to why when the second derivative equals 0, it's only a possible point of inflection a little bit later on, okay? It's something students often get messed around with on this, okay? So you need to be really, really careful, all right? So in this diagram, we have our point of inflection. You can see we go from concave down to concave up. And in this particular case, that would be where the second derivative is equal to 0. So, all right, we say that a curve changes concavity, all right, at a point of inflection, all right, so negative to positive, all right, or positive to negative. So our definition, and I really encourage you to put this in a red box, because this is probably the important and most pertinent takeaway from this lesson today, right, is that if the second derivative is equal to 0, and, heed my words, and the concavity changes, then it is a point of inflection, okay? Guaranteed. To add on top of that, all right, if you had the first derivative equaling 0 at the same point. Now, what does that mean? That means that you have a stationary point, okay? All right, at the same point as where your second derivative is equal to 0, then you have what is called a horizontal point of inflection, okay? So this one here is not a horizontal point of inflection because there is no stationary point on the original curve. Okay, however, here is an example of a horizontal point of inflection. You'll notice that our gradient of the tangent to the curve at that point is 0. So we have a stationary point there. And at that point there, you'll notice that we go from concave down to concave up on either side of that point. So it's both a point of inflection and a stationary point. All right, so we must have a horizontal point of inflection. I'll show you an example with that a little bit later on. Okay. All right, so essentially what I'm going to do in this particular video is I'm going to break this up into sort of 3 separate videos, all right, that sort of cover 3 key distinct examples for you to have a little bit of a look at. The first one being the most basic. There's no tricks or anything like that. It's just your most stock standard type of question in terms of just finding a point of inflection. Remembering this is like a precursor skill to sort of curve sketching, right? We're sort of building everything up and getting ready to do curve sketching with all of these different skills. Okay, so this particular question says, find the point of inflection. All right, that should be your hint in this question that you're going to find the second derivative on the curve, all right, which is x cubed minus 6x squared plus 5x plus 9. Okay, so in this particular example, I'm going to step this out step by step for you to try and give you a little bit of a scaffold, okay? So step 1, what we're going to do is we're going to differentiate, okay? Now, when we differentiate, all right, we find both the first and the second derivative, all right, because we'll need them anyway, all right? And so the first derivative, okay, differentiating x cubed becomes 3x squared, differentiating minus 6x squared gives us minus 12x, differentiating 5x gives us 5, and then the 9 disappears when we differentiate it, all right, because it is a constant. Then we know we're finding a point of inflection, so we need to find the second derivative. So going again, differentiating the first one, all right, 3x squared will become 6x, and then minus 12x will just become minus 12. Okay, so that's always our first step. Our second step then is to go and find the point of inflection. okay? And by finding the point in this particular case, I'm just going to get you to find the x value, and then later on we'll find the y coordinate for it as well. And I'm just going to sort of show you why I don't find the y coordinate immediately. You'll see it in example 3 that we do today. All right, so finding the point of inflection, okay, remember, all right, when our second derivative is equal to 0, all right, there's a possible point of inflection, okay? Point of inflection. Now, just being aware, there are different spellings for inflection. I picked the one with the x just because it's out of habit, okay? All right, so we're going to put our second derivative equal to 0. So that's a 6x minus 12 equals 0, just from what we found up here. All right, now we're just going to solve that. So we're going to add 12 to the other side, okay, and then divide by 6, and we end up with x equals 2. Now, we're not quite there yet, okay, because we actually don't know, and I really want you to heed my words on this. We don't know whether at x equals 2 we have concavity changing yet. We actually have to test that. So that's where we go to step 3, and we're going to test the concavity changes. So test concavity changes. All right, this is fairly similar to the first derivative test for classifying your stationary points. Okay, all right, so it's where we check out our x values in relation to our second derivative values around our point or points of inflection if we have multiple. Okay, all right, so we're worried about the point x equals 2 because that's what we've just found. All right, and so we know when we put x equals 2 into the second derivative, we end up with 0. So that's fine. Now what we want to do is we want to test points that are close to either side of x equals 2 and that don't go over any other stationary points or points of inflection, okay? There's only one point of inflection that we found on this curve. So I'm going to test the points that are closer to of 1 and 3, okay? Now, you don't have to necessarily write the working out for this bit, but I'm just going to show you what happens, all right? When I test the value of 1 in the second derivative, okay, I end up with 6 times, that's just coming from this one just here. I end up with 6 times 1 minus 12, which you can see immediately is going to be minus 6. So we have minus 6 in that box. When I test 3, f double dash of 3 is equal to 6 times 3 minus 12 is equal to 18 minus 12, which is just 6. Okay, I can do that in one step. So that gives us 6 now. All right. Now, just understanding for this particular point, why are we substituting these values in to the second derivative? Because that's testing the concavity at those points. So at this point, all right, for 1, we have a negative concavity. And at this point, we have a positive concavity, okay, which you can see in our diagram that we go from negative to positive here. Okay, I'm just sort of highlighting that for you in red. So because our concavity changes on either side of that x value of 2, it means that at x equals 2, we have a point of inflection. So we say, therefore, negative to positive concavity changes. All right, and we have to write this because we're telling the marker exactly what we're talking about. All right, concavity changes. Therefore, x equals 2 is a point of inflection. All right, and now we just do our final 4th step, which you can do as part of 3. All right, but our final 4th step now is to find the coordinate. Okay. All right. Now, why didn't I find the coordinate earlier, say over here, for example? Because it's not always necessarily going to be a point of inflection when I test the concavity changing, right? Sometimes the concavity won't change. And if it's not a point of inflection, I'm going to save myself some time and not bother finding the coordinate later on, okay? It's just sort of saving myself some work, okay? So I'm going to let x equal 2, and I'm going to put that back into the original function, this thing up here, because now I'm putting it into the original function to find the y value. All right, so we have, therefore, f of 2 is equal to 2 cubed minus 6 times 2 squared plus 5 times 2 plus 9, and that all comes out to, if you're using your calculator, being 3. And we just sort of conclude our answer off. We just do like a nice bit of wrapping up. Therefore, the point 2, 3, is a point of inflection. Okay. All right. So that's essentially the 4 steps to finding a point of inflection, right? You must differentiate, you must let your second derivative equal 0, and you must test concavity changes. After you've done that, then you find your y-coordinate and you're all good to go. Okay. In the next video, I'm going to show you an example in regards to a horizontal point of inflection, which follows much the same steps. However, you need to check the first derivative as well to make sure that it's not a normal point of inflection. Okay. All right. So I'll see you in that one. Okay. Thanks very much.